Thank you for having me here. You can go to the next slide. So today I will speak about our architecture actually for cross-sectorial, which is called like Cross-Sectorial Data Lab. And the main idea is actually deploy this application for solving of mainly industrial applications based on predictive control and predictive maintenance. So this architecture on the top level basically is just divided to edge operational platform, which is deployed directly on the shop floor on the particular factory, and it's integrated with all of these layers, and it's basically collecting data which are then used for the predictions using the predictive functions. But the predictive functions are developed in the cloud environment, Cross-Sectorial Data Lab platform, which basically just consolidate computational resources and provide collaborative environment for data scientists and domain experts. So we are collecting data on the shop floor using the operational platform. Then we are developing the predictive function in the Cross-Sectorial Data Lab cloud environment. And then we are deploying back predictive functions directly to some runtime environment on the shop floor. Next slide. So if you will take a look, I wanted to keep this schema actually quite simple, but it's not. Implementation is not so much. So this is the detail for the cloud part of our architecture. So basically, you can fetch data from the shop floors and integrate data. And this is actually quite important aspect, that we are not providing cloud platform just for the consolidation of the computational resources, but actually for the consolidation of the data. Because yes, you can have like a lot of raw data, but actually a lot of problems have like really sparse relevant data for the particular problem. So you need to consolidate sparse data actually to solve problem, and that's why we need a cloud platform even to consolidate data, not just to consolidate the resources and so on. So we are fetching data. You can get data in batches. This is quite convenient because you will not you will prepare some batch export and then you can upload all historical data to our cloud platform, or you can get real data directly from living operational environment. Then of course we have a data lake storage which is based on the distributed file system. If this is not enough for the data scientist, then the data can be lifted to a distributed database of different kinds. So you can use SQL-like interface, for example, for some reporting and aggregation of data, or you can use time series database to actually extract more complex patterns. Of course, then you need some computational resources, so you will have a distributed data processing framework for batch and real-time processing, where you are pre-processing data, building your predictive function, evaluating these predictive functions, and then after that, after testing, you will deploy this to model repository, and from the model repository, you can push this directly to your edge environment and run this in the production. Using the real-time data pipeline, you can actually even get measuring of model performance from the operational environment, or you can use this in more complex simulations. Then on the top, we are actually providing the development tools for the data scientists, and part of this is a semantic framework, and I will speak about this more in the next slide. Yeah. So here is just the overview of the technologies and open source projects, what we are using for the reference implementation of our platform. Mostly the core is, of course, based on Python or R language ecosystem, which is quite common for the data scientists. And then we have like distributed backend based on the Spark And data lake is implemented using the Minio file system recently, and we are using a combination of distributed databases, and we have some interfaces for batch processing and real-time communication. Okay, you can go to the next slide. So now I will speak about these semantic tools, which is the part of development tools dedicated for data scientists and domain experts, because the common way how to actually build predictive functions is to go through the different phases from problem understanding, data understanding, data preprocessing, modeling, evaluation, and deployment. And during this problem understanding and data understanding, very critical is actually knowledge which is shared between the data scientists and domain experts, because data scientists will have to understand like what is actually the industrial problem, what has to be optimized, and how this can be actually transformed to data mining tasks like classification, prediction, clustering, or anomaly detection, and so on. And of course, data scientists will need to identify like which data, together with the domain expert, will identify like which data are important to solve this problem. And even during the validation, domain experts will have to understand like what is the quality of the model and what will be the impact of model precision for the domain key performance indicators. So this is very important part from the point of view of knowledge sharing. And then the second part for the development of the predictive function is actually the coding. Like, yes, data scientists will have to write some scripts usually to pre-process data and to run machine learning algorithms and to build predictive functions, and then to evaluate this function, for example, by testing on some test set. And if you will take a look at this software work, let's say, it's really like a repetitive task because it's really like constrained by the data. So if you already know what is your data mining task, like if this is like classification, then this will determine algorithms, and together with your input data, this will constrain like what you have to implement for the data preprocessing, and after that, this will even determine like how the model can be like evaluated on the testing set, like which statistics are relevant for your problem. And you are doing this like repeatedly and finding and optimizing in the iterative way your models. But from the software point of view and from the development point of view, it's really the same code, and you can reuse the same code actually a lot for different problems. So what is the crucial is actually the knowledge, and the coding is boring actually quite well. Okay, so we want to actually build the tool which will simplify this process and will support both of these phases. Can you go next? Okay, so for sharing of the knowledge, we developed this environment where data scientists and domain experts can actually share the knowledge and can specify mapping between the domain problem and the data mining task, and can describe data elements and describe domain-specific key performance indicators like, okay, we want to optimize energy consumption or material consumption or whatever, and how we can actually map these to data mining tasks like prediction, and how we can actually relate these key performance indicators to statistics from model testing. And for the data scientists, we are providing the tool which will take the formal description of the data mining task, like if this is the classification, what will be the input, and what will be the predictive output, and how the model can be tested. Actually, we will take this formal description, and based on this formal description, we will automatically generate code by chaining of operators to fulfill this task and generate a script for the target programming language like Python or R language. And this script will basically just get data, pre-process data, experiment with the different algorithms and optimize in automatic way the parameters and get the best model basically. So this was fine. This was working quite well. Can you go next? Next one. And then we found that actually we can have different problems. And the first one is the problem understanding. If data scientists will not map properly domain problem to data mining task, then it doesn't matter that you will have like the perfect model with the perfect precision, but you are using this to solve actually different problem, and this will not work. Okay, this will be not efficient. Mostly the problem understanding is based on the narrative communication between the domain expert and the data scientist. And we found out that with the same description and with the same knowledge sharing, data scientists can have a different understanding of the problem. And we actually measured this using the experience, using the experiments with the data scientists, that with the same description of the problem, they can actually came with the different data mining tasks. So consistency is about the 80–85% between the domain experts, between the data scientists, and this really depends mainly on the experience of the data scientists. So we thought that, okay, can we use actually, for example, large language model to extract definition of the data mining task from the description of the problem, from the description which is provided by the domain experts, like textual description. Next slide. So what we like to do is we have like the problem description, which is really just extract, for example, from the documentation or from the notes collected by the discussion with the domain expert. And our goal is actually to use large language model to extract the formal definition of the problem, like what will be the task, if this will be the classification, regression, and so on, what will be the input data, what will be predicted, and which domain key performance indicators are related, and even which technical indicators are related for the specific task. Technical means like precision, recall, F1 score, and so on. So this is what we like to do. This is what we like to get from the textual description. So we use such a prompt and LLMs. Next slide. We have just collected, this is just a preliminary work. We have just collected 5 problems from different domains, like from the industry, economy, astronomy, and medicine. We have generated different variants of the text. So we are even measuring, like, if you will use the different formulation of the problem, how this will be related to our extraction. And then we are used the OpenAI GPT-4 to extract task definition for our problem using such a template. So you have like the example problems where we are specifying the description and the target task. And then you have the target problem, and you are asking about the formal definition of the task. So this was used to actually extract the outputs. Can you go next? And the preliminary results are okay. We have quite good precisions, and then we have measured like a recall across the domain, or if the problems were similar to what was in like an example. So for example, you have examples from the medical domain, and the target problem was the medical, and we measure like recall and precision for the final task definition, like how well we have extracted the task and input data and KPIs and so on. So the precision was quite good, definitely better than the consistency between a human data scientist. So this can be like a good supporting tools for data scientists and can help them to actually map different problems to text mining tasks. So we will see in the future. Thank you very much.
First of all, I have a kind of curiosity about that. So what is cognitive cloud from your point of view?
Cognitive is exactly that we are really extracting the formal description of the task from the cognitive communication with the domain expert. So usually, really, this problem understanding is really based on direct communication between humans, between the data scientists, and between the domain expert. So this is the main idea, that we like to support this part and extract this structured information.
Okay, that's interesting. It's yet another definition of those I was aware of. That's interesting. There are so many.
That's right.
Yeah. You know, I mean, this is like a hidden advertisement, but I cannot say it.
A lot of your talking kind of reminds me knowledge graphs, or that kind of providing structure on cognitive is kind of like creating a structure, at least to my mind, in the knowledge graphs. Do you have any comment on that aspect?
Yes, exactly. Semantic tools are actually based on the ontologies and knowledge graphs. So we have started with the formal framework, semantic framework and ontology to describe, for example, how to describe domain problem, how to describe text mining tasks, how to describe operators and algorithms and constraints from the operators and algorithms. This is actually the core of our automatic method, because we are using logical inference to chain operators and get the plan, and then we are just rewriting this formal definition from the ontology to executive code, like in Python or R. So we are using semantic technology, but to actually build a structure semantic model for description of the domain problem from these narratives, this is the main issue and can be inconsistent.
I was about to ask you, are you really using semantic models, or is it feature extraction? So that's the answer. But then I'm asking, you know, LLM, hallucinations, they are, you know, spot of inaccuracy. Whereas you want to map this to a solid, provably correct, you know, logic framework. So how do you deal with that? Does it happen that they generate or actually, what are they supposed to generate? So do they generate logic stuff that you can then check to see if it is compatible with the apps or the ontology? How do you deal with the ambiguity, right, of the output?
Yes, can you go back to previous slides, like that one? I don't yeah, this one. Yeah, exactly. So here you basically have input and data and output data. This is in combination. We have like library of data elements, and this can be like curated, and you can manually create like a definition of all data elements. Like, yes, we have this measurement and this measurement and this control signal and diagnostic signals. That's okay. So this is here, and you can actually even check this in your database and validate this. This is like close set of data mining tasks, like prediction and so on. So this is okay. This is domain oriented. Usually for us, key performance indicator is basically a data element. So we are even including this in our library of data elements, and you can even validate this. But yes, this can be more tricky to actually validate, because here you have more domain knowledge actually. So mostly, like I said, we are not. We are combining like what we have structured already with the description from the domain knowledge, from the domain expert. So there is still like a part which is created by the data scientists and so on. We are not using this just to throw the description and automatically generate code and run everything. We are not there yet. So far, it's a combination. This is what we are expecting from the model to actually extract. Okay, so if you will go next to next slide. Yeah. So what we are doing, you will have the set of examples. Then you have the description of your problem. Like, for example, I don't know, you are going to optimize, I don't know what. So this is what is provided from the domain expert, and then this is generated for the data scientist, and he can or she can validate this, and from this you have directly formal description of task for the code generation, and you can execute building of the predictive function in automatic way. So that's this part is quite okay.
Okay, the last question. It's like if I understand this still a very early thing because you have also a few test projects.
Yes.
Reliability of those task descriptions. I mean, if you ask several people at the same plant, they can do different things about these. What is the problem, and also with the same company, different rules and different terminologies for the same thing.
Yeah, we are not trying to solve actually what is the priority for the company to optimize and so on, or we are not speaking about fusion of domain knowledge, like okay, what should be like actually optimized and so on. This is really up to domain expert. But what we are trying to automatize is really even if you have a good understanding of domain and you know like what you like to optimize in your production, then you need to still transfer this to text or to data mining task, and to implement this using the machine learning and so on. And this transformation of optimization problem to the data mining task, this can be like ambiguous, and we are trying to support this part. Okay, but maybe in the future, yes, LLMs have potential to actually even support fusion on the domain level, and fusion of the knowledge on the domain level, and summarization on the domain level. But we are not doing this right now. Okay, this is really domain specific part.